Hey guys, John here with Knife Making Tuesday week 14. I'm finally done making my test blades. I've made 6, 7 of them, I don't know. These are the handles we're working with, titanium frame lock. Test blades, as you can see, this was already tested on this side, and then I did similar on the other side. And works awesome. It actually locks up. Don't know if you can see that, but it's got a tiny bit of lockup. I'm going to have to tweak tolerance one more time, but the next blade that I make is going to be a full blade, so that's happening next. It flips awesome. I find that the flipper lever is fairly pointy, and after flipping it 10 or 20 times and putting some good force on it, it feels pretty sharp. So I might round it over or something. My finger's starting to hurt, but flips great. Sometimes it doesn't go all the way out because this blade is so short. I mean, a full blade will be this long and have quite a bit more momentum to it. But the fact that I can, flip that guy out every time. And last week I carbonized the lock face, so it's not sticky at all. It disengages great. Detent is good. I think I'm going to tweak it a little bit for the real blade that I make. Could be a little bit stronger, but it doesn't fly out. So anyway, I got to go inside and write the code for my real blade, but should be done within about an hour. And then cutting that blade will probably take 45 minutes, maybe an hour. Okay, finally, a long time later, I'm finally ready to cut out my test blade. Or, not a test blade. I'm done cutting test blades. Next blade is going to be out of RWL34. It says 50 here because 50 is millimeters, 50 millimeters. So it's called RWL34. A lot of guys I've talked to have never actually heard of this steel. Very popular in Europe. It's a Swedish steel. I got this from Brian Ty. He loves to use it. He uses this and BG42 exclusively. So that's good enough for me right there. Jens Anso uses this exclusively. Alan Elishewitz uses this almost exclusively, he said. So it's awesome. I mean, there's so many blade choices, you can choose anything and it'll be a good knife. But in my opinion, why stick with the basic, 154 cm, S30V? When you have a choice, pick something cool. So this is going to be good. Let's go. First step, you can see I got the whole long bar in here. I've got a finger clamp down on the front edge, and I drilled 2 holes at the top. I'm going to bolt it down, and then remove the clamps, and then drill 2 holes in the bottom so that there's 4 points of contact on the blade. There we go, 4 points of contact. Not going anywhere, super sturdy. I've seen pictures from Jens Anso's shop. He made a bunch of blades on his new Haas CNC machine, and he's only got 2 points of contact, one at the front and back edge of the blade. So I'm going to start heavy duty with 4 bolts and maybe work back from there, but I'm liking the 4. Now before I get going, as is my usual tradition, I wanted to show off what tools I'm going to be using. There's the one I just used, this carbide spot drill to spot all the holes and do some chamfering. Little drill bit for the detent. 1/8 inch, no, what's that? 108 drill for the, thumb stud. And then some other drill bits and the reamer. And then what's really exciting, like super duper duper exciting, is all these collets that I just got in the mail yesterday from my good buddy Roger in Quebec. He made these for me special. I designed them, gave him the drawings, and he made these for me out of 4340 heat treated steel. I got about 24 of them. They are incredibly awesome. So anyway, that's another video. I'll do that on its own someday, but these are the rest of the tools that I'm going to be using, mounted up in their collets. Little 16th ball for engraving, big 1/4" ball for profiling the blades and doing the edge and stuff. 3/16 end mill for doing the outside profiling. 7-degree taper mill for doing the lock bar, and 1/8" end mill for doing some finish work. These are going to be awesome. Oh, I'm so excited. So, let's get all these drill bits out of the way, and then I can move to the fun tools. So I've got a few of the holes drilled already, all the holes spot drilled. Right now I'm going to drill the 3 holes for my jimping. They're 1/8" holes, but it turns out I don't have any 1/8" end mills, or sorry, 1/8" drill bits. I must have broken them all or something, and I don't have any more. So I'm going to use an 1/8" 2-flute end mill to plunge down in the holes, which I'm not totally comfortable doing. I think it'll work fine, but let's find out. It's not great to plunge an end mill like that, but I think it'll work. Yeah, it sounds fine actually. There we go. It's an old junky end mill anyway, so I didn't care about it if it broke. Yeah, that looks fine. That was no big deal. On to the next tool. This is a 0.17 drill bit for doing the pivot hole and the stop pin grooves. 0.17 is the perfect reamer size, or undersized drill for a reamer. So I've got my trusty 2,000-some-inch shim. I'm going to go down and go down 1,000th at a time until it stops moving. Since the shim is 2,000ths, I know that the thing is now 2,007-inch. So I tell the computer that, and then hit go. I've got my 3/16 reamer in here. I'm doing the exact same thing. Tell the computer 0.002. It's not the most absolute accurate way in the world to do it, but it gets me within 1 or 2,000ths of an inch, which for most things is all I need. So turn the speed down because reamers like to go slow. Hit go. It should be good. You can hear it if it's at the right speed. That sounds perfect. It's just a little squeal at the beginning and then nothing. So notice how I'm reaming 3 holes, not just the pivot. This is the test blade with the exact same thing as what we're doing. The pivot gets reamed for 3/4 or 3/16, and then this groove right in front of my finger and this groove are where the stop pins go. And I found that it works really good to ream those and then profile around. That way the stop pin fits in there perfectly. And then you can do the profile in and contour around and everything. Yeah, I found that works really good. And then you get a nice radius area for the stop pin, both closed and in the open position. So that works awesome. That's it for my drill bits. I blew through those in 10 or 15 minutes. That was pretty quick. So, and now I get to use my awesome collet holders that I got from Roger. So here's the first of my new collets mounted up in the machine. This is my little engraving end mill in it. This is basically what they look like compared to what the drill chuck was before. And they just slip up into the machine in a bigger collet that's got this same taper that fits in the machine. And then right now it's sort of a manual setup as far as tool changes. So I have to unscrew this this bolt on top, unscrew that, and then the tool holder pops right out, and then I plop the next one in, tighten that nut down again, and I'm back again. So eventually this will all be an automatic setup so that it'll actually change tools on its own. But that's a little ways in the future. So I got my engraving end mill in there. I still have to zero it onto the workpiece, and then we'll get engraving. That's all. Alright, so I'm using my engraving end mill to engrave RWL34 into the end of the blade. And I'm watching it, and it's cutting over the center of a hole. And I'm thinking to myself, you're not supposed to engrave there. What are you doing over there? Stupid machine. So I pause it. I go inside, look at my computer, SolidWorks, look at the CAD drawing and everything. And I found out that everything after this point, including the engraving and everything after that I still have to do, is offset from the part about, I don't know, 1/4 inch this way and 1/4 inch that way. And I remembered that as I was writing the code to engrave this, you know, I'm using the mouse and I click on the RWL words, and I accidentally dragged the entire thing in the program over and didn't notice, and I forgot about it. And so everything from here on out, all the operations are offset a little bit. So I just spent about 20 minutes. I had to go through all the operations from here on out and recenter them, bring them back to where they're supposed to be. And that's one of those little things that you have to go through every now and then. But so I got my little USB stick with the new code, and we'll get it loaded up and do some engraving. So it's a little bit of a pain to start a code halfway through the whole process, to restart it halfway through, but I'm getting pretty good at it, so go see what happens. Yeah, that looks good. As you can see, that turned out very nice. Very nice, very crisp, very sharp, no waviness to the cut at all. This end mill here, or this collet holder works awesome. So the next tool to put in is my 1/4 inch ball mill. This will basically grind the bevels of the blade, but it's going to cut them instead of grind them. So I'm going to use my awesome tool changer, manual tool changer, to change tools. So cutting the blade profile right now, or the edge geometry, I guess it would be. One thing I noticed about these collets is that because the meat of the collet is so close to the tip of the tool, any coolant flies up the tool and flings around. You can see how much spray I'm getting. And it's getting my floor wet, which happens. I mean, it's not a big deal, but that didn't used to happen on the old tool. But as you can see, I have my nice table here that I built, and I've got big walls for it. Actually, those pieces of plywood in the corner Those are going to be complete walls that will enclose the whole thing, and there'll be a glass front on the door that opens up. So that's going to keep all the coolant in. That's a future project that I've been working on for a while. Well, that turned out excellent. Really happy about that. Next up, I've got a 3/16 flat end mill. That's going to basically cut it out. What it's doing right now is it's cutting a circular bearing pocket. That's where my ball bearings are going to have to sit. Doing the finished pass right now. Going to lift up. It's going to go to that corner. It's going to come down at a bit of a tapered angle, and I'm going to try to do this. It's full depth of cut. Getting hot. Ah, crap. Ah, I broke it. Wow, broke a 3/16 end mill with a collet. Well, let's stop it. And I did not like that. That was kind of cool. Glad I got that on video. So I got a few choices. They're called speeds and feeds. Speed is the RPM that the thing's spinning at, and then feed is how fast you're moving the tool in inches per minute. My speeds and feeds were exactly what the GWizard Calculator told me to do. If you don't know what that is, go to cnccookbook.com. The GWizard is the foremost speed and feed calculator in the world. And I'm surprised that that broke a tool, actually. I know the creator of GWizard gets a kick out of watching my videos. He's probably watching this one at some point. And he might have something to say about that. So here's some aftermath. This is a new version of the end mill that I was just using. It's a Niagara. There's the part number, 85590, 3/16 end mill. This is a full length end mill. I'm curious. The stick out says about 0.8 inches, give or take, because I chucked it up to the collet right up to where the flutes start. So sticky outie was just over 0.8 inches. I told the program that the tool would only be sticking out 0.5 inches, which is this far, more or less. So you can see it had all this extra length to the left, and that's where it did all the cutting. And the more length you have sticking out, the more deflection you'll get with the tool. It'll start to bounce around and chatter. So my speeds and feeds were reliant upon a 1/2 inch stick out, and in fact it had, that, half of that again. I bet you that's what it was. This is the tool that broke off. You can see that there are there's some metal packed in between the chips, especially right, if I can get it to rotate, especially right here. Now that can't be good. So deflection is probably what broke it, but this chip packing is either chip evacuation, not evacuating, not getting out of the hole, or I don't know, what else could it be? I had flood coolant on it, so it's probably not that. I will go back to the calculator and try it again, compensating for the longer stick out. It felt like it was feeding really fast at 8.8, and it started to sound really funny and smoke and stuff. So smoke, Family Guy joke. So let's try it again. I would like to try a 3/16 end mill again, because knife maker Brian Ty said that this is what he uses exclusively for his all his steel and titanium cutting, 3/16. So I'd like to make that work. 1/4 inch just takes off a lot of material, and they're a little bit more expensive, and I'd like to make 3/16 work. Besides, a awesome guy on YouTube sent me a whole pack of these. They're lightly used, but I can't tell. So I'd like to make use of them. So here we have the GWizard Calculator. Wonderful program written by a guy named Bob Warfield from cnccookbook.com. When machining, there's lots of things, but there's two things you need to know: your speed and your feed. Your speed is the RPM that the tool spins at, and feed is the feed rate that the tool moves in inches per minute. It's sort of a black art to figure out these calculations on your own. And for me, a machinist who never went to school, I taught myself everything. This program is awesome. Just flat out awesome. I use it for everything. Anyway, I should do a review video of this later, but for now, I'll just get right into it. My blade steel is RWL34. You can choose from all these different steels: wood, titanium, aluminum, whatever. I just chose a 440A, annealed, with about 215 Brinell hardness. I have no idea if that's close to my blade or not, but that's what I chose. Carbide end mill, obviously, 3/16, 4 flute. Stick out is 0.5. Now I think here's where my problem lies, because the actual stick out of my tool was 0.8 inch. So stick out is 0.5, cut depth 1/8 of an inch thick, cut width, slot, the full width. If you look right here where my mouse is, it says deflection 0.004. That's how much the tool is going to deflect and wiggle while machining. Now if I move this up to 0.8, we go from deflection of 4 10,000ths to 15 10,000ths. From 4 to 15, that's huge. And you see it's in red. That red's basically telling you, whoa, it's going to break. And what do you know? It did break. My speeds and feeds are almost exactly, even at 0.8, they're recommended almost exactly what I used. Let's see, so at 0.5, yeah, I used 3300 and 8.1. And at 0.8, pretty much exactly. I think I'm feeding at 8.8, not 8.1. I forget why that is. Anyway, yeah, so with the stick out of 0.8, and I'm going to have to leave it there because that's how long my tool is. I can't really chuck it up any tighter than that. Maybe a little bit, but... So I got to find variables that make this deflection down to nothing. Let's try cut depth halfway down to 1/16 of an inch. Cuts the deflection in half. Let's try it even a little bit more to, let's say, 40 thou. Deflection is down to 5 10 thou. That's pretty much acceptable. 125 divided by 4, 3125. So if I did 4 passes down, deflection is down to 4 thou. Or sorry, 4 passes down. So if I used a stub tool, which is a tool that's, you know, very short, not 0.8 inches long, but more like 0.5 inch, then this wouldn't be a problem. So because my tool is so long, I'm going to have to do a shallow depth of cut. I can feed a little bit faster at 10.5, and there we have it. So I'm going to try these parameters and get back out there. So that was really interesting, looking at the GWizard calculator and figuring out that deflection and sticky outie were my culprits. So I got a new end mill in here, same exact one as before, with this is about 0.65 whatever inches of stick out. Before I had about 0.8. I was able to chuck this one up a little bit more. But you can see how much is sticking out there versus the width of the part of the tool. And you can imagine, since I'm only cutting, let's say, this thickness, you know, the very tip of the tool is doing all the cutting. All of this is just wasted space, just deflecting and bending and vibrating and chattering and all that stuff. So I found out that I can buy tools like this from IMCO, one of my suppliers, that are about half this long, half as much stick out. So you can imagine if it's only sticking out this much, there's like no deflection at all. So from now on I'm going to start buying those. But for now, this is all that I have, so I want to make this work. So I'm going to do 4 passes down, about 35 thou or something depth per pass. And it's going to take a lot longer, but whatever, it's not going to break a tool, it's going to be awesome. And for all you non-machinist nerds that might have found that last section a little boring, sorry it's a little long and stuff, but it's important to me that I get this information out of my head and, you know, out into the world. Maybe I help somebody out one day. So, because this is kind of what I geek out on. Knives and machining are my 2 things. So, let's move on. Let's cut. Sounds much better already. Yeah, it's having no problem doing these cuts at all. So this is 34 thousandths deep. We got 10.5 inches per minute, about 3,600 RPM. Much quieter cut than before. Tell you one thing I forgot to do that almost screwed me over was, you notice how I have 4 bolts holding the blade on either side. This top bolt up here in the corner will stay because the blade's going to be attached at that point. Right here at the pivot hole, I'm supposed to put a bolt in and screw it down, but I totally forgot. And I forgot to write it in my code, I forgot to make a note. Had I left that alone and it finished profiling, then the blade would have flopped all over the place and ruined it. So I'm glad I was able to stop it in time so that I can put the screw down. Finally, so that seemed to work really well. The blade actually has some shape to it now. This is my 7-degree taper end mill. Gonna cut the lock bar tang. Next it's going to cut my lock bar easy groove. This works. Ah! Crap! Holy. Okay, that didn't work. Wow! Son of a... Urgh! One wrong number in my code. That's and it looks like my end mill is toast. This is a $40 end mill. Or 35 or something like that. Grr! Well, I can still proceed with this blade. It's not going to have my easy groove, which is okay. This this divot that I just put in it is going to be a serious dent in the D10 travel, but that's okay. I can still move forward. Dang it! So right now I'm cutting some text. See, I flipped the blade over. Now we've got a fresh side. The profile looks awesome. That new tool and the new parameters I used worked really good. So right now I'm cutting the word prototype on the front edge of the blade. It should be just about done with that. There, it's doing the E right now. Go back for a little touch up, and then it's going to do my logo right there by the thumb stud. That's going to take a while. Let's speed this up. Now this is kind of interesting. So I've got my ball mill, my 1/4-inch ball mill in the tool right now, and it's going to cut the edge. And I'm trying to zero it on the surface of the part. So I started zeroing it here, and then I thought, well, it'd be smart to zero it on the edge area, just in case it's different. And I'm finding that this area right where my thumb is, or my finger, has actually bowed up quite a bit from the two bolting points because they're very far away from this corner of the edge. So it's flexing, and I can actually push it with my hand. Hopefully that shows up in video. And I can see it bending down a noticeable amount. So I think I'm going to have to start putting a tab right about there, a third tab. And between the 3 tabs, they should be good. It should be very well held down. So that'll be version 2. For now, I think I'll just zero it on, not quite the highest spot, maybe the middle. Maybe right about here somewhere. And then it'll sort of average out. Some parts will be thicker or thinner than the rest, but I doubt you'll even be able to tell. But in the future, if it's held down in a 3-point arc, it'll be perfect. Alright, so it's been a very long evening, but finally all done. Just time to pull it out of the machine and take a closer look. Before I pull it out, I just noticed that there is no slash in the R for prototype. So now it's some weird prototype. So before I pull it out, while it's still zeroed in, I'm gonna write a quick piece of code to write that little line. I've had that before with my R's, I don't know why. SolidWorks or SolidCam ignores that little line. So I'm gonna do that real quick and then I'll pull it out. So here we have it, folks. This is the blade we just made today. Quite a few little mistakes, but nothing major. This easy groove problem was very unfortunate. Absolutely destroyed my $35 tool. For reference, let's see here. Like this little 1/8" end mill, I can get for about $7. So a $35 end mill is a lot. And that tool should theoretically last forever, but not if you break it. So I left the tab here that I can then break and sand off afterwards. And as you can see, ow! Okay, so it breaks off, not bends. Luckily, no blood. Wow, didn't see that coming. I thought it would bend right off. That snapped. Durr. Anyway, there's the blade. I tried a different style of linear machining, or constant Z machining I should call it. Here's the one that I made originally. Notice it's got a very, very tight group of lines. And then this one has a much broader group of lines. I noticed that Brian Ty does all of his, or a lot of his knives with a bigger space between the lines. Please post a comment, let me know which you like better, because I could go either way at the moment. I'm not super in love with this exact pattern. And the big obvious thing are all these dents in the middle. And you get them a little bit right here too. What that what's doing that is how would I say, looseness in my milling machine table. As the part's moving, you know, it's got 3 axes of movement, or 2 really, front, back, left to right. When it's moving front back, the screw that leads it forward and backwards has some play in it. So it's got to kick it back before it keeps spinning and then kick it and pull it this way. Anyway, what that does is it causes these dents, which are very visible. You're not going to Scotch-Brite those out. You're not going to sand them out. Those are there to stay pretty much. Same on the other side. And that's something that I will fix and deal with on my machine. More parts to buy. Other than that, and that groove problem, I've got one of the best profiling finishes I've ever had. There you can see a dent right there, same problem as before. But edge finish is one of the best that I've had yet from this little machine. Edge thickness turned out very consistent, throughout the entire thing, which is a problem I was having with this one. Notice how this is practically a zero grind, like right off the machine it was this sharp, and I could almost cut myself with it. But this time I did much better, and I left about 20, 25 thou. I was shooting for 20 thou. But remember how the part was bowing up a little bit, so the fact that I'm getting 20, 25, 15, whatever, that's fine. So again, let me know which grind, let's call it, you like better. The upper one here with the very tight lines, or the bigger step over. And then here's blade I made at the same time as this one. I gave it a really cool stone wash using the poor man's stone wash. We're talking ceramic stones in a peanut butter jar with 1 drop of soap and some water, and you shake it for about 2 minutes, and it came out like this. That looks pretty cool. Anyway, so real quick, I gotta put it together. I'm gonna sand it down on my marble plate with some sandpaper and put it together. Alright, a few initial observations. This is the last test plate that I made. Here's my easy groove. It just helps the detent ball get up in there. The detent hole right here, this is a 1/16 of an inch. On this one, I drilled it up to about 2 millimeters, which is exactly the same size as the hole. And I moved the location. So now there is a little bit of closed blade play, which is unacceptable. That's okay, I can change that. And I did not chamfer the detent hole, and it's, I could move it, but it's nearly impossible. Way too tough. So I made a note of that. Anyway, here is what it looks like. Wow. I polished the blade up using WD-40 and started with 220 grit, finished it off with 600 grit on a flat surface. And wow, against those bronze handles. Oh, and something I did earlier today that I have never done actually. These are the screws I'm going to be using. Very nice screws. That's what they're going to look like installed. All these washers and crap are just for testing because the screws are too long actually. That's how slick they're going to be, how smooth they're going to be, how elegant they are going to look when this is all said and done. You can't even feel it. Everything about this knife is going to be that nice. I don't know why a screw makes me so excited, but it just makes me really happy that it fits and it looks good and it works good. So I got the blade out. This is my detent hole right there. I'm just going to take a bigger drill bit and just manually put a chamfer in there for testing purposes. Because like I said, it's impossible, nearly impossible to disengage it. This would be faster on the machine, but I don't know how deep I want it, so I just got to tweak. Ta-da! So the detent action is maybe the tiniest bit better after chamfering the hole, but basically I need to move the whole location over and possibly stick with the smaller hole. Anyway, now remember the mistake hole from my easy groove problem causes the detent to lock right there. It's got 2 locations, which is sort of like you know how jackknife stops in the middle and then stops at the top. But and lastly, there's some serious blade play up and down. Just let me get some light on here. Put it on low. Oops, cut it too deep. I did make a pretty noticeable change in the lock bar between this last test blade that worked. This one worked quite well, but it locked up way too early. It had like 1% lockup. I'm shooting for maybe 10 or 20% or something. And I changed it, cut it too deep. So that's dumb. Even if I bent the lock bar all the way over, still the tiniest bit. That's okay. This is still technically a test blade. That edge geometry pattern looks pretty neat, all said and done altogether. So if it locked up properly, and if it didn't have these dumb bumps in the middle, and the detent wasn't so hard, it's pretty awesome. Yeah, those few problems that I just mentioned cause it not to open up as nice as it could, but it's getting there. Cool. That's Knife Making Tuesday week, what are we, week 14? This has really dragged on. Amazing that I could do this after week 4, maybe even week 5. But of course it doesn't work and there's lots of problems with it. This is a much more elegant design. So it's taken me 10 weeks to get from here to here. And a layman might not see the difference, but everything has improved. And another thing I want to do is put a recessed thumb groove on the inside of the lock bar here. So when you're digging your thumb in, I find that this one's kind of sharp and hard to reach. So, and I changed the profile of the flipper lever from my test blade to this one. My test blade one, it was hurting my finger after playing with it all day. So I rounded it out, shortened it a little bit, made it a little bit higher, and that's very comfortable. I love ball bearing knives. I'm getting there, people. Thank you for your patience, and thanks for all the comments and watching the channel and everything, support. This is a lot of fun. I don't know if I'm getting better at this particular knife or if it's breaking in or something. I don't know. Maybe the detent is breaking in. Yeah, it is for sure. Keep in mind this blade has not been hardened, so it's gonna wear both on the lock face, on the detent hole. The ball bearings are gonna dig into it. You know, once it's hardened, then it's gonna last forever. But until then, this is just garbage test. Not garbage, museum piece. Cool. And last thing I need to figure out is a pocket clip. I would like to make my own pocket clip. I was going to use those ones, the ones you can buy from USA Knife Maker, the titanium ones. But I want to make one. I think I'm going to go for tip down because it's a flipper. So pocket clip is going to bolt here somewhere. It's going to go down to there, be something really nice. So it slips in your pocket. You pull it out like this and flip it. Take some practice. So if it's tip up, you got to pull it out of the pocket like this. You got to move your whole hand to get it out. That is breaking in nicely. The whack. Anyway, that's it for this week. This is probably quite a long video by now. Really appreciate the support, guys. Not sure what I'm doing next week, but it'll be something cool. Fine tuning, spacers, pocket clip. Thanks, guys. Take care. Bye.